All right, we are now in the last section of Perspective Matters. So this one goes along with homework 5 in Lumen. So if we talk about scientific notation, the idea behind scientific notation is that we either want to write really, really large numbers or really, really small numbers in a standard form so that it's a little easier to understand versus writing all the zeros. So if we look at the mass of Mercury, for example, it's this big number, and we really can't comprehend that compared to Jupiter's mass and which one is bigger and so forth. So what we would do with Mercury's mass to write it in scientific notation is we would take the first number, which is the 3, and then put a dot. So there's always only one number in front of the decimal. And then what we would do is write the rest of the non-zero numbers. So we would put the 301 right there. And then when you get to all zeros, instead of writing them over and over and over again, we write them as a power of 10. So what we would do is we moved the decimal from the end all the way to the beginning at the 3.3. So we would count how many times we moved it. So we moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 15, 18, 21, 23 times. So we would put that as 3.301 times 10 to the 23rd power. And now that tells us that that decimal has another 23 essentially zeros behind it, and we can kind of identify that as a very large number. Now, if I go down to Jupiter's mass and I count those, again, we're going to start with one decimal, so just that first number. So I'm going to write Jupiter as 1.899, and then we're going to count how many places we move those decimals over. So 3, 6, 9, 12, 15, 18, 21, 24, 27. So Jupiter is actually to the 27th. So that's a power of 10 to the 4th larger. So 10,000 times bigger, but it wasn't as easy to compare them. So what we're going to do now is kind of write that in a way that makes sense in this box. So if I want to move something to the ones place, so write, 2 or 3, but make it a power of 10. It would be 2 times 1 gives me 2, or 2 times 10 to the 0. So the way we write our ones place is we write it as, so we would write this one as 10 to the 0, which represents a 1. If we want to change and make 20, that's the same as 2 times 10, or 2 times 10 to the 1. So the way we represent a 10 is 10 to the 1, which is 10. And then we keep going. 10 squared means 100 2 times, so that's 100. And if you want to write 1,000, there's 3 zeros, so 10 to the 3rd, 1, 2, 3. All right, now going backwards, think of these also as moving decimals. These are moving your decimals that many places to make a bigger number. So if I have 10 to the 27th, I'm moving it 1, 2, 3, all the way down. For the decimal places, though, we're moving the decimal the other way. So think for a second to this white blood cell that I have down here in the example. So over here on this white blood cell, instead of trying to figure out all those zeros, we start by taking the first number we see on the left, and that becomes the first number, put a decimal, and then we put the 5. So we start when all the zeros stop, and then we're figuring out how many places we moved that. 1, 2, 3, 4, 5. So that's 1.5 times 10 to the negative 5, and that represents a small number. So think if I have negatives, I'm going really small. And now we can compare the mass of Jupiter to a white blood cell is quite different in magnitude. So to do that, if I have 10 to the negative 1, that's the same as 1 over 10, or 0.1. So that's saying multiply your number like a 2 times 0.1, which moves the decimal over 1. So if I want to represent a tens place, I do a negative 1, which moves it over 1 spot. If I want to do a hundredth place, I do 2, which represents 1, 2. So it's how many spots it got moved. So thousandth would be negative 3, 1, 2, 3, and then so forth and so on until you're all the way through. Okay, so on that idea, the scientific notation lets us write really small or really large numbers in an easy to understand way and compare. So very quickly, yeah, a white blood cell is much smaller than Jupiter, than Mercury, and we can order these, on a number line. The smaller the number, the smaller the item is, and so forth. So going down, when we write scientific notation, there's always one digit, just one, in front of the decimal. So if you have a really big number, you keep going from left to right until you have all zeros. When you have a really small number, you go left to right when you hit the non-zeros, and then we're going to move back and forth depending on how we do it. So when a scientific notation number has a positive exponent, or that's 10 to the 1, that's our 10 to the 2, that's like multiplying the number by 100 for 10 to the 2, so that's going to make it bigger. So for that, if we have a positive exponent, think that we have a number greater than 1. And then if we have a negative exponent, like 10 to the negative 2, that's like multiplying by a decimal. So you're going to have a number that is between 0 and 1, a smaller number. Now we don't do negatives in this. That would just have a negative in front. So negative exponents just mean a really small number between 0 and 1. There should be a between in there. So then going backwards, if you're trying to write a really large number greater than 1, the exponent you're using should be positive. And if you're trying to write a really small decimal, the exponent should be negative. So you don't necessarily have to memorize this, just kind of keep in mind what would make sense. If I'm writing a really, really small number, I'm going to use a negative number exponent and so forth. So just kind of grasp that idea of scientific notation. So we have quite a few examples we can try. So this first one is if I have a mass of a particle dust. A particle dust itself is going to be really, really small. We can't see it. And this negative 10 definitely tells us it's really small. So I like to come over and write the 753 that I already have. And what this tells me is that this decimal is moving 10 to the left. 1, 2, 3, 4, 5, 6, all the way through, which means I have 9 zeros in front of that 7. And now I don't have a decimal anymore. So 9 zeros after the decimal, and then I have the 753. Now what this 24 tells me, and again, mass of Earth is going to be really, really big, is that I'm moving 24 decimals to the right. So I'm going to write 5, and then the 9 counts. So 1, 2, 3 of my 24. So then I have another 21 zeros I need to write. Okay, let's see if we can fit them all. There we go. So just to make sure you wrote enough, that's going to be 21 zeros. So I have my initial 1, 2, 3, and then the other 21 zeros to the right. So pretty large number versus a really small number. You can see why you would want to write those in scientific notation. So then over here, I have the mass of the Empire State Building. So again, to start off, you always have one number in front of the decimal and only one. So it's going to be 7.3. And then we count how many places it got moved. 1, 2, 3, 4, 5, 6, 7, 8. So it already becomes hard to tell. Okay. So pretty heavy. Then if we do the thickness of hair, it's 1, 2, 3, 4, 5. Because remember, I have to move it so that one number is in front. And then it's a small number, so it's going to be a negative. So it was a number between 0 and 1. At this point, pause and try the rest of them. And I'm going to keep going. Okay, so when we're trying to compare numbers, where the actual exponent falls is what you should look first. Bigger exponent, bigger number. If the exponents are equal, that means each of these have 5 more after the decimal. So if they're equal, we don't really have to worry about them at all because we're just comparing a bunch of zeros now. And it's a little bit easier to compare it that way than this way, but it might be easier for you to see either way. So this 4.8 is bigger than 3.4. So that's the way it's going to go. Then if I come down here, the 6 is much bigger than the 4. So that one's the bigger one. And then coming over here, 6 is bigger than -6. -4 and -3. -3 is bigger when we get into negatives. So on a number line, if you're not sure, put the numbers on there. And that way we can compare them pretty easily. The -3 is bigger. And then here, 9 is bigger than 8. So we can compare it that way. So then when I'm looking at these, which is the greatest, I'm looking for the highest exponent. And if some are the same, then I would look at the actual number. But that's 8, 7, 8. The 9 is the biggest. I'm not even going to worry about looking at those. And then when I order from least to greatest, this is where a number line is pretty helpful. It would go 4, 5, 6. There are 2 4s, so I would pick the smaller number first. So 4.08 times 10 to the 4. Then 5.1 times 10 to the 4. And then go in order of the exponents. 1.23 times 10 to the 5. And 7.9 times 10 to the 6th. And I've got them ordered. So again, least to greatest. Down here, we would do -4, -3, 5, 7. So that would be my order. So it'd be -3 times 10 to the -4. 5.6 times 10 to the -3. 9.01 times 10 to the 5. And 2.3 times 10 to the 7. And then we've got those. And then finishing up our question, which is the smallest, means we're looking for the smallest number in the exponent, and then the smallest if there's a tie. So Mercury is going to be our winner here for smallest diameter. And then let's see, is an antibody or a flu? -8, -7. That actually means that the flu is 10 times bigger than an antibody. So the flu virus cell is bigger by 10. And then if you have time, go ahead and check out what we have here. It's pretty cool. It just shows the sizes of common objects and different cell types. And it's a pretty interesting one to look at. So you are now ready for homework number 5 in Unit 1.